Log on, tune in, find out. Another good idea from Cambridge.
Thanks to all the organizers for inviting me here. We start with a very general kind of problem. Suppose you have a sufficiently smooth coefficient function appearing as a potential in a wave operator. So the most general kind of, sort of the simplest kind of model of an inhomogeneous modeling wave propagation in an inhomogeneous medium. So let's denote by u of xt and xc the solution of Lu equals delta function with singularity xc and with zero initial conditions. So this is just one of the standard the standard fundamental solutions for the operator L. And the question is, can we determine the operator, that is to say the coefficient function q, from suitable measurements of u, and u as a function of some subset of the variables xt and xc. So there's some measurement set which is in the 2n plus 1 dimensional space, which I'll call sigma. So all the possible values of xt and xc. So there are many familiar and not so familiar special cases of this which have been studied over the years. I'll review several of them in a few minutes. Obviously, the measurement set sigma is going to be somewhat lower dimensional than 2n plus 1 to have an interesting problem, but not lower than n, because n is the dimension of the dimensionality of q. Of particular interest to me will be the case when the dimension of sigma is exactly n. This is the so-called formally determined case, so the least possible, a case of the least possible dimension of the information. And there's various questions that one should ask for questions like this: uniqueness, the stability, how could you compute the solution. In this talk, I'll only be talking about the uniqueness question. And the specific problem, which I'll get to after some discussion of the background, is joint work with Rakesh. And it'll be the following formally determined case when the measurement set sigma consists of the following kinds of points. There's xc, remember, is the source point, so the source will be only the single point 0, and then the measurements will be taken on a sphere centered at the origin and for some interval of time t. So that is 3 dimensions of data. And we're going to wish to determine q on one side or the other of the measurement sphere, x equal to r. If we're thinking of q as being unknown for x bigger than r, then this we would think of as a reflection type of problem, because the source and the measurements are on the same side of the medium. And if q, the other problem, which I'll get to if there's time at the end, is when q is unknown for x less than r, and that would be a transmission type problem, because the waves have to travel through the medium to get to the measurement set. In the usual way, one tries to define this in a precise mathematical form by defining a coefficient to data mapping. So just for a given q in some suitable space, we consider the mapping f from q to the restriction of u to the measurement set sigma. So symbolically, we write the problem as an operator equation. This is in general always a nonlinear map. In the best possible world, for the question of uniqueness, we would want to show that f is a one-to-one mapping between the suitably chosen function spaces, and these should be the ones that are defined only by physically realistic assumptions that one might make. Now, we're rarely so lucky, as in our work and in many other most other works. Some additional assumptions are made which you'd rather not have there. So here are some representative results that show the kind of restrictions that have been made to get somewhere in problems like this. First of all, in the case of one space dimension, so let's assume that the potential q is just 0 in the left half line, and then the measurement set consists of all the points 0, 0, t. So it means that the source is at 0, the measurement is at 0, and we're just measuring for some interval of time. Okay, in that case, one knows that q is then determined up to the time capital T over 2. That's the best you can do based on finite time of propagation considerations. The sound speed is 1 in this case. First result of this type, I would say, it appears in the work of Krein and then elaborated in various ways by Glachensky, by Bill Symes, and many other people. A closely related three-dimensional result, well, a result in which the space dimension is equal to 3, but the coefficient is assumed to only depend on depth, okay, in one dimension, which we'll call AX3. So let's assume still that Q is 0 for now in the upper half space, X3 negative, and the data set will in this case be the set of points of the form x star xc star t, again for some t interval. X star and xc star are now two fixed points on the surface, x3 equal to 0. So any two fixed points with third coordinates equal to 0. So just any one receiver on the surface of a half space and corresponding to any one source. And then in that case, Rakesh has shown that, again, uniqueness holds in suitable function space up to a time which is, again, the best you could do based on finite speed of propagation considerations. This is really a sort of trick, a mathematical trick here in which this problem is reduced to this one. It really uses the three-dimensionality, so as far as I'm aware, this corresponding thing has not been done, say for when n is equal to 2. All right, let's go on to some more generally higher dimensional situations. When take the three-dimensional world again, and suppose that Q has support inside some bounded convex region, which I'll call S. So the measurement set in that case, let's say, consists of putting points, sources and receivers at all points on the surface of S. Okay, so I know U, the response at any point on the boundary of S in response to a source at any point of S on some time interval. And then it can be shown that Q is then uniquely determined inside of S provided T is sufficiently large. And you can find at least some early result of this type in say, the book of Laurentiev, Romanov, and Shishkovsky. There is a similar result using only one source. Okay, so I won't take only one source, Xi, but X is all over S, provided one has two other conditions instead. That is, one is, I think this is just a technical condition that could be done away with, but there's some sort of a sufficient separation between the one source Xi and the measurement surface S. But second assumption that really is necessary is a smallness assumption, that the potential one is trying to determine is sufficiently small in some space. I think it's L infinity. I might mention, although it doesn't quite fit into my general case, the similar result when one has the wave equation operator, that is a coefficient C instead of the potential form coefficient, again when n is equal to 3, and you suppose you have knowledge of the entire five-dimensional data set. So you have C equal to some known constant above the surface, and C decays to that same constant sufficiently rapidly below the half space x3 equal to 0. And then you measure at every point on the surface, again, so sigma consists of all sources on the surface, all receivers on the surface, and in this case all time, infinite time. And in that case, C is uniquely determined also. So the difference between this case and the previous case is that you're not really surrounding the medium in this case. You just have the bounding plane. So this work is often attributed to Ram, but basic idea occurs in an earlier paper of Lavrentiev. And the last specific case I'll mention is, again, for n equal to 3, Q equal 0 for x3 negative. And take the case when the measurement set consists of all the cases when sources and receiver are at the same point, so-called backscatter case. So xt when x is a point with third component equal to 0. So again, on the x3 equal to 0 plane, we consider all source points but receivers at the same points. In this case, for the exact problem I stated, as far as I know, there is no uniqueness result known. But if you linearize this problem In particular, you linearize this with respect to the constant background q equal to 0. The problem that you get is equivalent to the much more well-known problem of determining a function from knowledge of its spherical means. So even for example, if you even look in Courant and Hilbert, you will find some uniqueness results about this. So in particular, if q were assumed to be even with respect to the x3 equal to 0 plane, then it's known, at least as far as this approximation goes, that delta q, the small perturbation in q, is uniquely determined by the corresponding small perturbation in G. All right, so from those results, you have the following conclusion. The uniqueness results have been shown provided one or more of the following kind of conditions holds. And there's lots of other results that follow on to the ones I've mentioned. But they all tend to fall into one of the following categories. One is that the unknown coefficient depends on only one variable. It's not important that the wave propagation be in one dimension, but it's the dependency of the unknown coefficient that's on one variable only. So lots of results known in that case. Second is the problem is overdetermined. Okay, so the dimension of the data set is definitely more than the dimension of the unknown. There's another set of results that are valid when the unknown coefficient is small in some sense. Many, many more results when the problem has been linearized. It doesn't have to be with respect to the 0 background, as in my example, but linearized in some way. And finally, if the geometry is such that sources and receivers surround the region of interest. So these are all sort of more favorable situations where one can get further. So now, the problem I'm going to describe doesn't actually have any of those restrictions, but it has its own unfortunate restrictions that you'll see in a minute. So here is the reflection version of the problem that I mentioned several slides ago. So we're in n equal to 3, and we want to determine q in the exterior of the sphere of radius r given data on the sphere of radius r. So the source is at the origin, and we measure on a surrounding sphere up to some sufficiently large time, and then we want to determine the coefficient q outside the sphere. And clearly there's going to be some limitation on how far away you can go because of the fixed finite time. So in the end, you're going to be determining the coefficient in an annular region. So in fact, if you just see what finite speed of propagation tells you, you'll quickly convince yourself that the best you can possibly do with this kind of data is to determine the coefficient up to the outer radius r plus t over 2. Okay, so as I mentioned, there will be a different kind of restriction which occurs here, and this has precedence in the literature too, which I'll explain after I state the theorem, having to do with restriction on the angular dependence of the coefficients. So I have to set things up a little bit. So by introducing some notations. So SR will be the surface of the sphere of radius r, and any time a function q appears, then there can be a corresponding function p that you get by averaging it along lines from the origin to the point x. There's now going to be a certain set of functions, and in the end, this will be a function for which serves as a constraint set. So it'll be q sub gamma of r and t. So r and t are the radius of the sphere and the time interval introduced early. Gamma is a certain constant which appears in the condition I'm about to state. So these are C2 functions q for which a certain inequality holds. So the equality is defined in terms of the p instead of the q for convenience. And these are norms on the sphere. Okay? So this is h2 of the sphere, so angular derivatives up through order 2 on the sphere. And angular derivatives up to order 1 of the radial derivative on the sphere are bounded by this fixed constant gamma times some lower derivatives also on the sphere. Okay, so h2 here, h1 here, h1 here, L2 here. This is supposed to be independently of little r over the range, the relevant range of radiuses. Okay, so it's a function. It's a property that a function may or may not have, belonging to that class of functions. So here is the theorem. So r, of course, should be less than t. Suppose I have two potentials which are of class C8. Now that's certainly too much. I'll comment about that in a minute. Suppose they coincide inside the sphere of radius r. And suppose the Dirichlet data for those two different q's, that is the Dirichlet data corresponding to the same source at the origin, as measured on the sphere of radius r, so they are the same. Okay, so that's the measured data. And then here is the unfortunate extra assumption is that the difference belongs to this constraint set for some value of the parameter. Okay, conclusion is then you have the uniqueness that Q1 and Q2 are the same in that annular region. All right, so comments about the assumptions that are made. The C8 assumption, this was just, we want to know that the solutions that we're working with are classical solutions in the closure of the interior of the forward light cone. And this was just the easiest assumption we could make, so we could quote a result from the literature that guarantees that that's true. This is surely more restrictive than necessary, but at least in this book of Romanoff, it seemed to be the least restrictive condition on Q that we could make that absolutely guaranteed that condition to be true. Now, the constraint condition that the difference of the two Q's belongs to this funny set. So what's that all about? It's roughly speaking restricting the way the variation with respect of the coefficient with respect to the angle variable theta compares to the variation with respect to r. So the worst possible situation would be if you have a lot of variation with respect to angle theta and very little variation with respect to r. Best possible situation would be when you have most of your variation with respect to radius and very little with respect to the angular pairs. So in the limit, it only depends on r is the best possible situation. And this kind of condition, as I say, appears in various guises in the literature. The formulation we use is very close to the kind of setup that appeared in a paper of Bill Symes from the early 1980s. This was for a half-space geometry, so instead of angle, you have the horizontal variables, but the idea is similar. Very frequently in the Russian literature, you find conditions like this, that the coefficient that you're trying to identify has this finite sum of products form, in which so this would be for the half-space geometry. You can imagine what would happen for the spherical case, but you have dependence on the distinguished variable n multiplied by some other dependence on the horizontal variables, the orthogonal variables. So this is of a similar nature. And functions of this type will also satisfy the kind of restriction that we make. I might also mention a recent paper of Michael Klebanoff in which it's not exactly the same kind of problem, but he also is sort of forced to regularize in the horizontal directions. And he does that by essentially replacing the derivatives, the horizontal derivatives, by finite differences in those directions. And so that's of the same flavor as well. All right, so let me just give a few ideas in the proof. The proof is, well, we want to get the delta function out of the problem in the first place, so we use the well-known kind of expansion of the function by subtracting off its most singular part. So you can replace the delta function source by saying that in the interior of the forward light cone, it's simply a solution of the homogeneous equation, of course, and then with a certain condition on the light cone itself, and that will turn out to be this type. Naturally, we go to polar coordinates and look at the equation satisfied by the difference of the two solutions that we're interested in. If you do that, you get in polar coordinates a setup like this. So v as a function of r theta and t, the difference of the two solutions satisfies this. So omega is just a symbol representing all of the angular dependence. The details aren't important here. And so inside, the difference satisfies this kind of equation inside the light cone and a certain condition on the surface of the light cone, where again P and Q are related in this way. So the proof is essentially a use of energy estimates. Now, with energy estimates, there's sort of the standard estimates in which T is the distinguished variable. But we also use a variation of energy estimates in which the radius is the distinguished variable. And this is normally not to be considered a true energy estimate. I mean, it isn't really, because when you do this, what you'll end up with is terms that you can't control. They're not controlled by the sort of data terms that you want to control them by. But that is exactly the point where this special constraint set comes in. That constraint allows you to estimate the terms you can't control in terms of ones that you can control. And again, this sort of sometimes goes by the name of sideways energy estimates, and this also originates in the work of Bill Symes, first in the one-dimensional case and later in the multi-dimensional case. So as I say, terms which can't be directly controlled show up, and this is where the constraint gets used. So for example, this is just after some steps in the calculation, you get to an inequality like this, and it just shows terms of the types you want to estimate, because what I'd like to show is P equal to 0. P equals 0 is uniqueness. So I'd like to get an estimate which allows me to show that P is 0. And it's estimated by some other stuff, and here you see very dangerous looking terms. These are gradients of second angular derivatives. Sorry, not first derivatives, not second derivatives. So these are second angular derivatives of P. And you just don't know what to do with those, so that's where you use the constraint. That allows you to estimate terms like this by terms which already appear on the left-hand side. You can then swallow them up into the terms on the left-hand side by taking advantage of the fact that this coefficient can be made arbitrarily small. And then, now that coefficient being arbitrarily small means T minus R is small. So this is not the general case yet, because that's a restriction on T that I haven't already stated. So, but you do get at least a local in radius uniqueness statement that way by taking T minus R is sufficiently small. But then you can make a continuation argument. You could propagate both the coefficient and the wave field to the next radius and then repeat the argument. All right, so my time is about up. There is a related linear uniqueness theorem in which you don't have this special constraint, but it is the linearized problem and not the general problem. And this is also restricted by the fact that when you linearize with respect to a radially dependent background only. So in that case, there's a corresponding result. And then in the case of the transmission configuration, so we're measuring data on the outside of the sphere and trying to determine the coefficient on the inside. There is the following partial uniqueness result. Q1 and Q2 are smooth enough with the same Cauchy data. And here's the main point. At least one of the two candidate solutions must be sufficiently small. Okay, so if you have two candidate solutions with the same data, and at least one of them, there's a delta such that at least one of them is smaller than delta, then they must be the same. Okay, so it's a little better than requiring them both to be small, but it's still far from being the general result. And the linearized version of that problem, uniqueness was already proved by Romanov. And the general problem seems to be is still open, even in the 3D case, obviously, as I just stated. But in fact, even in one space dimension, if you write down the analogous problem of what I just stated, even in one space dimension where things tend to be much easier, then the unrestricted uniqueness result is, as far as I know, still an open problem. And I'll stop there. Thank you.
Do you have similar results for wave equation where you are interested in the velocity instead of the potential?
Yeah, that's harder. Yeah, not for this problem. I mean, the whole geometry would have to change in that case. So we're really using the fact that the wave speed is constant in this case. So the new result here definitely is nothing like that is known as far as I know for variable velocity. Some of the earlier results, the one-dimensional results, are certainly there are variable velocity versions of those, and in some of the cases of the early results, there are variable velocity versions. But sometimes it's an important difference, and sometimes it's not. And it's,
Okay, there's a question.
Can you drop your delta function assumption?
and replace it by some more general localized source.
Well, make it band limited, like
Band limited. Well, as far as uniqueness goes, if it's as long as you can deconvolve to get the delta source,
Yeah,
then,
if you call
then,
it-
that doesn't change the fact of uniqueness or not. If obviously you have to do something about the source, can't be zero. If it's not deconvolvable but not zero, then that's some intermediate situation which I couldn't say anything specific about.
I asked the question to lack of efficiency.
Mhm.
I had a discussion with lack of efficiency with an
Ah.
interpreter actually.
Yeah.
But he couldn't answer either.
Yeah,
It's very hard. I mean, the earthquake that generated the tsunami in Thailand and Indonesia,
Yeah.
in the Indian Ocean, that was the
Yeah.
only one that was like a delta function because it excited the lowest frequencies in the whole Earth. But that's not the kind of source you can use in practice.
So you think of even an unknown source, or you think of a known but non-delta,
But no low frequencies. In
no frequency.
So you can't be convolved.
Just as a mathematical fact of uniqueness, well, it can't be deconvolved. Yeah, then these results just aren't applicable.
I just wondered if anybody would ever care to look.
More questions? No?
Do you think there's a good chance that there's a non-uniqueness result in that case?
A non-uniqueness result for
In other words, two Qs, band-limited source with, say nothing in 0 to omega positive. We could build two potentials that give
literally
exactly
nothing.
the
Is that
same
consistent with a
response.
causal source?
Causality would kind of get in the way, wouldn't it?
If it's causal, then Hardy space theory would say that you can't have that kind of situation, I think. Practically speaking, it's not, you can't deconvolve, but by using analyticity, then you could probably still prove there can't be a counterexample.
However, I bet we could build a sequence of media that were as close as you like
Mm-hmm.
and gave the same response, as close as you like.
But that's a different source, right?
Yeah.
Yeah. So you had these quite high regularity assumptions that you hinted were technical.
Yeah.
Is there any known counterexamples for really bad regularity?
Not that I know of.
So probably these are just technical.
Yeah.
Okay. Thank the speaker again.